Hey guys, how's everybody going? Sorry I'm a minute late. We're trying to get stuff fixed. We had a little connection difficulty, so I wanted to try and kind of recable my network connection here to try to get rid of some of the static. We have some strange noise problems. So let me mute everybody. Okay, I mean, even with everybody muted, we could hear things. So I don't know if it was my connection, but we're going to try that and see if it works. All right, we had left off, oops, in the middle of this section here. So let me pull this up and then I'll share my screen and we'll get started. So I'll pop over here, take one more peek. L3, I think we were like at 68 or 9. Yep, we sure were. Okay. So I can still hear people. The mute is not working on the WebEx. It's just so strange to me. I don't know if we'll get through 4, but let's pull it up. Maybe we'll get lucky. So you're muted by default when you come into WebEx. When you came in, if you hit the mute button, all you did was unmute yourself. So you'll want to go back and take a peek, see if the little microphone icon is red with a line through it, and if it isn't, try tapping mute again, and it should mute you. Okay, so we are ready to get going, and I'm going to share my screen. And thank you, I appreciate that, guys. Okay. Yeah, I see some people are still trying to get this thing to show up. That's the same thing that was happening last time. So there must be something going on with the WebEx server a little funny this afternoon. So we'd gotten up to this slide last time on network security and things that were being attacked. So we'll go very quickly through this because I put in many more slides than we will actually need. I just basically took an entire presentation I gave to the department last year on what's going on with network security attacks these days, and we'll fly through some things to try to show you the things that are going on. So software is one area of attack, and the software that we're talking about when we talk about people hacking into and trying to bring down programs is running up typically up at the application layer, but software runs in every other layer. So check your microphone. If you hit the mute button when you came in, you unmuted yourself. I mute you by default. Once I join, I mute everybody by default. So, okay. So I can hear car noise or something like that. So I guess I need to go look and see who it is. Okay, Hien, you unmuted yourself. Please mute yourself back again. Or I can, I'll mute you. There, I muted you. All right, I got you. All right. You're muted, so you're good. So we'll come back over. It's tricky, and I wished it worked better than this, guys, so I apologize for that. But sometimes the software that we're talking about runs in these other layers as well. Okay, somebody's unmuted again. Quit touching it. Let me do it. No touchy. I will mute you. Don't touch it again. I got you. All right. So one of us has got to stop. And then sometimes the software is at these other layers. So these are programs that are running in other parts of the operating system. And some of them are programs that are actually running in firmware. And sadly, sometimes people figure out how to hack this stuff too at the bottom. And when they do that, it usually destroys the equipment, and you have to toss it out. There are attacks that go around now that are targeted specifically at those vulnerabilities, particularly things like BIOS in your motherboard for your Intel system, for example. BIOS does things like tells the system where to go look for the operating system. It tells it where the initial startup boot port is, and so that's something you don't ever want to that you don't ever want to have somebody change, because if that ever changes, you permanently lose your ability to boot your computer. And so that's like a forklift upgrade. So lots of targets, lots of places where people can try to attack things. But the ones that I want to kind of highlight today are generally denial of service attacks. So they fall into a variety of categories. Here's a little more of the list of what I showed you. And then I'll talk briefly about amplification attacks, but I'll come back to that at the end. So let's look at a few simple models of attacks. A direct attack is kind of the dumb one. This is like punching someone in the face. They know who did it, and they'll come to get you. So if you attack somebody directly from your machine, then it's obvious what IP address did it, and they can come after you. A more clandestine way of doing it is for the attacker to figure out how to compromise other people's systems. Okay, what issue are you guys having with audio? What's it doing? Be more specific, please. So you can't hear me? Okay, some people can hear, I think, right? I can hear you. I mean, I can hear noises once in a while. Yeah, there's a button to enable the audio. So when you join WebEx, which you haven't done before if you don't know how to join audio, there's a separate audio join place. You either have to grab it when you first go in or hunt for it, because it's a dialog box that says, you know, now you need to join audio. So look for an audio button or a microphone, and you'll want to connect through the computer. That's the way you're doing that. If you're using Firefox, it should still give you like a microphone or a little audio link. If you're running the app, it's going to be on most platforms on the top sort of thing. So thanks. Okay, you guys got it. You'll be helping them out. Yeah, you kind of outed yourself at not being in audio and not being in WebEx yet. All right, so a more clandestine way to do this, probably, unless it's screwing up on you, you can infect a different system owned by somebody else, and these then become compromised. And my systems have become compromised before because I'm an idiot at not keeping them up to date. Used to. I'm better now, I promise, I think. So what happens here is you don't even have to touch anything. It's not like you click on a phishing email link or click on a page that you weren't supposed to. This could be more subtle than that. This could be, you know, like me not applying a security patch and or having a laptop that I keep around but I leave turned off for a year, and I pop it back on and start using it, and the first thing that happens is I get hacked because I haven't applied any of the updates, because there's like 20 of them that wants to do it at once, and I'm trying to get something done quick, and somebody installs software that I don't know about, and it may never affect my performance. I may never be aware that it's there. It may go away on its own. It may not. But what it does is, on a botnet attack, it's been given instructions to perform a task. And the types of tasks it can perform vary, but the idea is that they're going to launch an attack at a target. So if you are brute force, then you'll just start like doing things that are just painfully obviously attacks. Illegitimate URLs, emails that are full of garbage, whatever it might be. A more subtle and more difficult way to attack somebody is to send what look like legitimate requests for service, like, may I please see the homepage of your site? How much does that iron cost that you're selling on your website? Can I bid on these following items on eBay, or browse around and look at them? But you do it in such volume because there's so many compromised systems that it's a much bigger load than the user was prepared to accept and that they normally would see. So this would have to be, if it's an important site, then it probably has resources, significant resources, and so your attack's going to have to be huge, or it's just going to bounce right off of them. They'll be able to just ignore, they'll try to hand you web pages back as if you're legitimate, and they won't notice anything. They won't break a sweat doing it. But if you can figure out how to get enough systems compromised, then you can overwhelm the target with requests. And they can't at first tell which are the good ones from the bad ones, so they can't just do things like shut it off for everyone, because then they really have succeeded in getting you, bring yourself down. when that happens. That's getting harder to do because people have more resources, so a more current twist is to do something called an amplification attack. And this is one where you send the request to some systems. These don't even have to be PCs at this point. You can send these into routers, for examples. And these don't necessarily become compromised systems as much as they become accomplices. And so an example of an amplification attack would be to drop a packet on the network that makes its way to a site, and the site takes as the truth what's inside the packet. And inside the packet might be something that says, the following New York Times site has requested a copy of this file via HTTP. And so he goes, yep, you got it, I'll send it. And so you start sending this massive file. So you didn't have to send the file. You got somebody else, the place that has the file, to send it. And if you can get a similar request into lots of other people, now the very little bandwidth that you have has been amplified into massive bandwidth that's now flooding at this target. That's much harder to beef up for. That's way in excess of the kind of traffic that they would assume. So the idea is these accomplice systems gang up for you on the target. So it's a very famous example of this done last year, about this time, where GitHub, which is an open source software site, they were attacked at 12:15 p.m. The timeline is Greenwich, so don't worry about the timeline. Sort of ramped up, pretty quickly. You can see some things happening, and at its peak, there was 1.35 terabits per second of data flooding into their systems. There's no way they can handle it. It just totally oversaturates, and it's one of the biggest attacks anybody's ever seen before. So it was an extremely successful attack. It's extremely successful amplification attack in particular. But look how short it lasted. 5 minutes, and then the fun was over. So how? What happened? What did they do? Well, they turned to the resources of a partner, and they had 100,000 web caching servers, people around the internet who keep copies of popular web pages so that their users don't have to go to the original source for everything and can instead get lots of their content that doesn't change very often from a local site, like most of an eBay page or most of the Houston Chronicle page. I mean, there's some things on the New York Times page that don't change at all, like the logo, the masthead, the section for here's all the sections in the paper at the bottom. And then there's some things that only change once a day, like the crossword puzzle. And there's some things that change every 4 hours and then every 1 hour. So the web caching servers cache these things, and they're told when they make copies of these objects how long it's safe to hold on to them before they should go back. So the whole pages, some version of the page is out on lots of these websites because those big newspapers are popular. So just drop a packet at the web caching server that says, hey, GitHub just asked you to send a copy of that page. And so it does. And then you send it, do it again, do it again, do it again. And you do this to 100,000 web caching servers, and they turn around and flood what is the equivalent of 1 million users pumping contents at, and it's a much bigger content than you normally would expect to get. At GitHub, you're looking for like people clicking on links, downloading files, and instead you have all this massive data. So it's easy to spot that it's not legitimate, but it's a denial of service attack. So it's not a botnet running malware. It's just taking advantage of an administrative loophole where the web caching server believed that the request was coming from one of its users, even though it was coming from the internet. They shouldn't have had that open. So we've fixed that. But how did they keep from getting overwhelmed? Why did it only last five minutes? They had a partner that has servers and ISPs all over the world, Akamai, and they run content delivery networks. And one of the things that these guys do is they offer this DDoS mitigation service. So once you're being attacked, if you have a contract with them, then it's very quick to get done. You basically say, I'm being attacked. They will send entries into the world's directory services to tell every ISP GitHub has moved. It's no longer at GitHub. It's now on this server right here in your ISP. So any traffic that comes in, starting right now, trying to get to GitHub, send it to me. And they'll accept it as the truth, and they'll funnel all the traffic. So this server has much less to deal with than GitHub does, which is good. They only have one server there, but it's able to deal with what's coming from that one site because they've scaled the number of servers based on the number of users. So they can see what's coming in, and they're quickly figuring out the fingerprint of the attack. Oh, it's web pages coming in. Well, that doesn't make any sense. Those are easy to spot. So they write a little rule. They push it out to all of their servers and say, okay, you know that stuff that's coming in from GitHub? Filter everything that looks like this out and let the rest of it send it on to the real GitHub. So within 10 minutes, they'd figured it out. They'd put in the rule. They'd intercepted all of GitHub's traffic and were throwing it all on the floor at the ISP. It never even impacted the internet after that. So throwing an extra 1.3 terabits at the internet is also hard on the internet, but it's impossible for GitHub to deal with. So that was a huge one for Akamai, and they wrote about it, and they wrote too much about it because they basically said, well, that's the biggest we could ever handle. I don't think if it was 1.5 terabits, I don't think we could have done anything. Well, guess how big the next attack's going to be. Way to go, genius. So it's fun, and you wonder if they're telling the truth with that, or if they know exactly what they're doing, and they're sort of playing with people. But that was a very considered a very big success story and a template for how businesses should prepare for the inevitable denial of service attack. You need to have a mitigation partner to do it. And sometimes if you're just so big like Google, you are the mitigation partner. You're your own partner. So no one can have enough servers to overwhelm you. You're King Kong. So that's kind of the idea. All right, so that's more or less what's going on with the attack stuff. We don't need to go through tons more. To get back to a few pages that the book has, they basically define it as you select a target, you get a bunch of systems to gang up on them for you, and then you send packets to that target. Okay, we talked about Wireshark. You guys have played with it. It does packet sniffing. You can just listen for packets and try to debug what's going on, but there's a more sinister way to use this stuff, and one of them is shown here. You intentionally position yourself between a source and a destination, and you advertise to this guy that you're him. Or you otherwise can find a way to grab his traffic before A gets a hold of it, and at the very least get a copy of everything he's doing. But if you can actually manage to insert yourself in the middle, then you can masquerade as him. So think about going to the Student Center here at U of H, and you walk in, and there's some people with tuxedos on with order tablets and a tablecloth on the tables, and you're like, wow, what's going on? And you go, like, it's the Hilton Hospitality School graduation service, and so to thank the students here for supporting them, we're serving you lunch. Oh, wow, isn't that nice? So yeah, I would probably fall for that. So they take your order. They have a copy of the menu from each of the places, Chick-fil-A and McDonald's and et cetera, and you pick what you want, and they ask for your credit card, and they just going to walk it over. Nope, I'm not going to run your credit card. I'm going to just take it over to them. Just give me a moment. They walk up, and they give the credit card to the restaurant, but maybe they pad a few extra things on there. Yeah, and a chocolate dipped ice cream cone, please, or an Oreo something. Or they just copy the numbers down. And McDonald's thinks they're the customer because they do all the things a customer would do. They order, they pay, they walk away with the food. So McDonald's notices nothing different. And then the next thing that happens is you think they're McDonald's because they kind of told you they were, and you gave them your order and your money, and you got the food, just like McDonald's does when you go there. So you can have these man-in-the-middle attacks that are very difficult to detect and very effective. So properly run networks look for intruders. They look for anomalies. They have their switches and their routers working in conjunction, which is a big argument for having them all from the same vendor and all managed with the same platform. So if they see hardware addresses moving, or if they see one duplicated, it sets off alarm bells. And they may disable, by default, most switches, if they see the same hardware address show up in two places, they will disable the new one and send a check packet or whatever they can come up with. If they shut off both of them, then all you have to do is flood the port with everyone else's hardware addresses, and you just get the switch to shut everybody off. That's an attack too. So this is done at a layer below us. This is done more with monitoring and hardware software. Okay, so to take a peek very, very briefly at some of the history, we don't have enough time to go through this as deeply as we will as we do in some of the more advanced courses. But if we get time in the end, we may, we may come back to it. But there's a couple of things worth mentioning here, and I'm very confused by an interview interpretation that Wired magazine gave to a conversation they had with Paul Barron, whose name is mentioned here. Paul Barron wrote a paper. He's had lots of successful inventions, including spread spectrum wireless and the basis on which some of the cellular technologies work. He's kind of incredible. Some of the stuff I had no idea he had anything to do with until I'd read this Wired magazine. Somebody's managed to unmute themselves, so I'm going to mute them back. All right, there we go. But he's most famous for writing a paper as part of the RAND Corporation, laying out how you might have a network that currently is run from a central location, and you communicate to individual stations. And so think of these as missile silos, because that's what they were. And think of this as the general at the command center in Omaha, Nebraska. And if the Russians blow up, one of these lines, you've lost the ability to launch a counterattack because you can't talk to the silo anymore and tell them do it. So they looked at lots of different mechanisms for using AM radio, using FM radio. There were some amazing things that I've got to go back and read again, but the interview I just found in the last day or so, it was done some years ago. I sort of stumbled across it looking. But what the publisher, what the editor said, I think is a total misinterpretation. And it's not what Paul wrote in his original paper, which I've read over and over and over. And he said this was not designed in response to a desire to withstand a nuclear attack. That's exactly what it said. It was designed to withstand. So it's interesting reading, and if I'm correct, I may have dropped it out there for you guys. It doesn't look like it's there, so I'm gonna grab it really. That's the wrong folder, so that's one part of the problem. Let's see, students, articles. It should be there. Let me see if I can find it in here. That's Agrawal. I need Barron, so let me grab it for you. It's sort of terrible that I don't have it in there for you. Let's see, here we go. And we'll quit out of this and drag it into here. So there's an article now by Paul Barron, and it's his original paper on coming up with this idea of breaking things into packets and putting addresses in each one of them so they can be independently routed, and sending them whatever route is available and up and running to do it. So you can see things like survivable. Survivable from what, Paul, if it's not a military attack? Military concerned with automating functions, needing to transmit data. We can continue on here a little bit. Enemy attacks directed against nodes. Now, how the heck is that not a military attack? Excuse me. So I think he forgot a little something, or I'm like very confused. But I'll throw the Wired article out there for you guys as well. But I think I pretty much know how to read English. And he said basically it wasn't the USSR. The biggest threat was the phone company. Oh, baloney. So anyway, some interesting stuff out there if you want to read some of that. I'll tell you, the history back then is changing every year right now because it's been long enough that people realize it's their last chance to kind of get their proof, get their papers, get their old copies of conference proceedings, old photos they took with people on stage. And he does a lot of this. He's very evidence-based. So he says, I've had people that have denied they were ever even at a meeting with me and stuff, and that they ever learned any of this, and yet I have lots of meeting minutes that showed I was chairing meetings and they attended, like dozens of them. So like, how can they say that they weren't in there? So he's pretty detail-oriented, and it's a very interesting read. So if you have Wired, then you can go look for Founding Father, and I'll drag it out there for you guys otherwise. So we'll just skip the rest of the history stuff because we missed a lecture with Martin Luther King Day, and I don't want us to fall behind. And it's just interest. You're not going to get a homework or an exam question on it, but I would encourage you to take a peek at the book in it because it's definitely fun. Okay, so to continue on, we need to take a look at now moving into applications. So remember, we have the 5-layer protocol stack. Please do not take advice. Physical data link, transport, network, and application. And we're going to start at the top and work our way down. So we have applications that we all use every day on the internet, like HTTP. We probably are all aware that we use that one because that's the protocol that we probably recognize as the one that we use for web browsers. It's the name of the language that governs the exchange of information that we have with a web server. And it establishes which one of us is the client, and therefore what rules we follow, and which one of us is the server. And it takes us all through step by step. We looked at the RFC earlier in the semester, kind of glanced. It's 170 something pages long of thrilling text. Every page is a page burner. Not. But it's the name of that protocol. HTML is the syntax of the web page, but it is not the format of the language that is used to exchange the web page, to exchange those pieces of information. That's different. English may be the language on the paper inside the envelope, but you have rules that are different about how you get the letter to me. You need an envelope with no more or less than a certain size and thickness and weight. Postage goes here. Address must be formed like this. It needs a 5-digit zip code if it's a U.S. address, etc. So some of those words may be in English, but it's not what you would call the letter. It's different. They're separate. FTP is for file transfers. Sometimes when you click on links, like if you're on a Google page and you see links to things like PDFs. So I think I can show you one. Here's a couple of PDF papers on circuit switching, some Stanford stuff I was reading. And this one will directly download a PDF file. If I click on it, it's not going to open a web page. It will FTP the file down and bring it directly to my machine. And so here it is, right? So here's that paper. So that's a protocol that I'm using that I may not even be aware of, but I'm using it. This one's email, and your phone uses this. And if you run Gmail, you're causing that protocol to run back in Google servers, but it shows up to you just as a web page, so it's just HTTP as it gets to you. And the one that we run constantly all day long, hundreds of times a day, is DNS, and some of us may not have even heard of that. A lot of us may not have heard of that before. So we're going to take a look at those. Most of the things that you use are running at the application layer. So we'll take a look at how do you write a program that actually gets stuff into and out of the network. So those protocols and lots of others exist to help us run programs like this. Everything from streaming video, social networking, text messaging, web pages, emails, and so on. So to create a program, to create a so-called network app, you take an application and you add commands that make function calls to functions that are included in a special I/O library called the socket library, and Berkeley socket distribution, BSD, Berkeley standard distribution. There's socket. They have lots of different names for versions. They used to call different releases of these things the same names as the Berkeley releases because they distributed them at the same time as Berkeley released new versions of Unix to the world. In the old days, AT&T, who created Unix, owned the license, and if you were lucky enough to learn about it, you discovered that you could get your hands on a free copy. It was very expensive otherwise, and businesses that wanted to use Unix had to buy it from Bell Labs. But for schools, they gave Berkeley University the permission to distribute it to educational and nonprofit institutions for essentially nothing. And TCP/IP was a growing popular networking protocol that more people wanted inside of Unix. And so they sort of teamed up with Berkeley, and every time Berkeley was going to issue a new major release of that version of BSD Unix, TCP/IP would take whatever updates they had and include it. So they were joined at the hip like that for a long time. So people got their updates for TCP when they got their updates for Unix. And so this library was included. And the only thing you needed to do was learn how to make calls to about 4 different functions, and that was about it. And the functions weren't difficult. They included things like pass me an argument telling me the IP address of the computer you're trying to reach, give me a couple of settings to let me know the details of how you want the connection to work, and then pour the data at me. Give me as much data as you can in this data structure size I've defined, and if you need to send more than that, then send me another one. Call me again. And so that's the way it would work. And if you're expecting to get something back, then I'll tap you on the shoulder, and then you need to be running a listening. You need to call the function that waits and listens for things to come in from the internet, and your communication protocol will tell you when it's time for you to do that. So after you send an HTTP GET request, you run the function that waits to listen, and you wait for the packet to come back, and you go grab it. So this is the way things do. It's not hard to do. It's just a few function calls, 5 minutes, and you can be messing around with it. So you don't need to write software for any layer underneath that. 2 basic models, client-server and peer-to-peer. Client-server is what we mostly use for things like websites and downloading software, etc. But the problem is scaling. And by that I mean you can overwhelm things with denial of service attacks. We just talked about that, right? So you need to be able to handle whatever load the world's going to get at you, and it's a great way to control what's going on. Everything comes back to one place, but it makes you vulnerable. And for lots of websites, they couldn't handle even the legitimate load. If you're a poetry publisher and one of your poets is named the Nobel laureate of poetry, and suddenly you have more than 2 hits a week, which is all you got before, and now you've got 100,000 hits in an hour, what prayer do you have? And so we'll talk about what happens when that starts to occur. So one of the responses, if you know you're not going to scale well, or there's nobody who's willing to set servers up in an expensive data center for you, is you just don't use this model at all to begin with. And instead you use a peer-to-peer model like BitTorrent, where there may be a server to kind of point you at the users, but that's all it does. It just gets its packet to you, and that's done. It's a very, very light load, and your connection is directly with other systems. So it scales infinitely more quickly and largely because it's not all going back to one bottleneck location. It self-scales. It's murderous on the telecommunications providers because they're expecting most of the traffic to go in one direction, and now you're like turning that upside down on them for half the sites. And it's very resilient. So what we find happening, like I say, when people go in opposite directions, lots of times they look back at the other party and they go, some of the stuff they did is actually really smart. We could do that too. And they borrow from each other. So sites like peer-to-peer sites do have some servers to try to coordinate what's going on. So they're not totally peer-to-peer. And sites that are all client-server will push things out to a peer-to-peer network to help with scale, like mitigating the DDoS attack. that we saw a minute ago. They basically turn themselves into a P2P architecture for 5 minutes by distributing their site, boom, to like 3,000 locations. Okay, try beating up on 3,000 of me. So it's like you've cloned yourself. All right, the idea behind this essentially is you've got processes communicating, and there's been ways in Unix for years to communicate from one process to another inside the same system. So one way to view these socket libraries is they've just taken those procedure calls and extended them across the network now. So you just run whatever the procedure was that the program you were talking to before, and now you can run it on a different computer. And I've given you the software that will tie your two computers together for those two processes to communicate. That's a much simpler idea to get your head around if you already know how to have one program pass data to another program, not so much like a subroutine, but like independent procedures. And that's not tough code to write either, but it's easier to understand how this networking concept works, and you start assuming some right things about data structures and models if you know how to do that. So the process is just a program running inside of a host, and you can have two processes using IPC or inter-process communication. If you separate them by the network, then it becomes a set of clients and servers instead. So the processes on different hosts will just basically group what they want to send to each other into messages and send it back and forth that way. So this socket is a piece of software that catches whatever the application throws at it. It's a function call that you make, and it will take care of registering your program's interest in using the network with the rest of the stack and keeping track of who you are exactly. They'll assign a number to you, a port number, and then things will leave. They'll get to the site. If something comes back for you, when it gets back to the machine, at some point the stack is going to say, okay, we know it's for this computer, but which program do I give this to? There's like 1,000 programs running on this system. Which one? And the socket steps up and goes, I recognize that number. It belongs to my program. Hand it to me. I'll give it to them. And so you've got lots of sockets running at the same time to try and implement reliable delivery. So to keep track of things, you've got to have some way of uniquely identifying your process. And on systems, we use process identifiers. So it's this column that I'm showing you here. There's like hundreds and hundreds running on my computer. I couldn't begin to tell you what most of them do. But so those are the numbers that this socket software is going to keep track of. And because different operating systems and different hardware have different ways of numbering and naming their processes, that's not specified in an RFC because they can't force, there's no reason to force hardware manufacturers to change their end systems. It's not a network thing. It's just a process ID. Not all processes want to use the network. Why would you ask them to change the way they do process ID numbering for the network if they're not even network? So that's not going to go anywhere. So we will accept whatever process numbering scheme you've got, and we'll map it to a similar addressing scheme that is part of the RFC, that is part of TCP/IP, called a port number. Right? So the computer itself also needs an address. So if you tell me the address of the computer and the number of the application, between those two things, I can get it to the right place on the internet and to the right program in that place. So both things are important. For the machine part, for the big part, we use IP addresses, and we use port numbers for the actual program by program piece of it. Right? So does an IP address where a process runs, is that enough? Well, no, we just talked about that. It gets you to the right computer, but this is like showing up with an envelope at Cullen Towers and saying, here's an envelope, it's got your address. And they're like, okay, but which apartment is it for? I don't have that. Well, then I don't know who to deliver it to. Well, I got it to the right address. Well, not really, because we have apartment numbers here. So if you don't give me the second part of the address, then I'm not going to accept the packet, and it'll get refused. That's exactly what will happen if you try sending a packet and there's nobody listening on that port number, or the port number is not one that it recognizes, or that process has crashed and there's like nobody to answer for the moment, etc. So both parts are critical for anything that needs to get its way up to the application layer, because you can have many things running on the same host. So we use that 32-bit process. The port numbers you may have seen before. Web servers typically run a process that listens for incoming connections that are trying to reach it on port 80. Well, how does everybody know to try to reach the web server on port 80? Tradition, because it got so popular, it was given a well-known, meaning permanent, port number. So your browser, if you type in a URL and hit return, it'll go figure out what the IP address is, so it'll do that part, and then it'll just assume that it's going to be port 80 that you're trying to reach unless you tell it otherwise. You can type in more characters into the URL in your browser and change the port number that it tries to connect to, but by default it's going to connect to 80. Email will by default try to connect to port 25. And there's a whole list of well-known port numbers that you can find out on the internet, well-known port numbers, and hopefully TCP/IP guide comes up early. I'm going to see if I can find his stuff because he's got some awesome website stuff. Yeah, here we go. So this used to be a book for a long time, then became a website. I think he's kind of stopped updating it, but it's extremely readable, lots of good examples, absolutely free, and voluminous. So he's got dozens of pages of examples and tables and things like that. So here's some well-known port numbers. So let me look for 80s right here for HTTP, and port 25 we said was for email, simple mail transfer. 21 is for FTP. If you run the POP email protocol, it runs at 110. Network time protocol is 123. Oh, that makes kind of some sense, doesn't it? If you're running HTTP over secure sockets like HTTPS, that will run over port 443 and on and on and on. All right, so we have lots of these things that are out there. We'll learn more about port numbers soon as well. Okay, so the protocol, going back to the RFC and reading the definition, that application layer protocol, we needed to do things like govern when it's time to send a request, when it's time to send a response, who goes first, who should start listening in the morning, waiting for people to connect, what port number should they listen on by default, what syntax is valid, semantics, what the meaning of things are. If they send me back a 3, what does it mean? Well, what was the last thing you sent them? Well, I asked them for the number of pages. Well, then it's the number of pages. Well, no, this time I got a 3 back. Well, what'd you ask them for this time? Well, this time I asked them what language number do they speak. Well, 3 means English, so it means they speak English. So, the syntax has all got to be laid out there. And every program follows a protocol, but they're not all published for everyone to read. It's like some people file patents to disclose how they invented something. The problem with filing a patent is now everybody knows exactly how you did it. And you are basically warning them not to copy you by giving them notice, but you're also inviting them to copy you if they think they can get away with it, aren't you? So if you are 3M Corporation, you publish no patents. Everything you do is a secret. So how you get that glue onto the paper, their whole business, their patent attorney told me when he was my customer once that their business is basically buying things from one person, smearing something on it, and selling it for more money. So that's the way sandpaper works, filtration masks, polarizing window coverings, Post-it notes, adhesive tape, scratch and sniff. Those are all 3M inventions, and that's exactly what they all are. So they don't publish patents. They keep things secret. And so does Skype. They don't publish their protocol. They keep it they keep it a secret itself. So the socket library, a socket is an instantiation of a set of routines and data structures that go along with them that implement the channel through which your program can pass data to the transport layer in the TCP/IP stack. The port number is the identifying number given to that instantiation. So if there's 500 programs talking on the internet on your computer, they each will have a socket, and each socket will have a different port number. Generally, there's some exceptions, but that's generally the way to think of it. All right, so every time you open up a browser window and you go to a different place, you're opening up another socket to a different computer on the network. If you open up a web page that's got things coming in from 10 different websites, then you're going to have 10 different sockets open. It may not let you open all of those at the same time, and it may have a different way of managing it through just one socket. But those are things that people have tried to improve over time. So there's a variety of transport services. Most people use one of two, TCP or UDP. And which service do you need? Well, if you need something to give you a hand in keeping track of your packets, making sure they don't get lost, keeping them in order, retransmitting them if they do get lost without bothering the application again, and only letting the network handle so many packets at a time before you decide it's not doing very well, and slowing down so you don't overwhelm anybody, asking permission before you start sending things, lots of things like that. Then you want to use something that gives you things like data integrity and maybe timing, maybe throughput. So you can try to map up the services you need to whichever one of these works best, TCP or UDP. But neither of them are a perfect fit, so there are always some gaps. And for lots of applications, particularly ones that need security, you're going to have to write that yourself or add in another library yourself to your own code, or get the operating system to install another library that adds security for everybody, or something like that, because TCP and UDP don't do anything at all with security. Right? A little bit on error checking, but nothing like encryption, nothing like that. So you can categorize apps and characterize what kind of service they need. File transfer, it's something where generally you will tolerate no loss. You expect no loss. Throughput is elastic. What that means is if the first half of the attached file to your email takes 5 seconds to arrive, and then there's this mysterious 2-second delay, and then the other half of it takes 10 seconds to dribble in, no problem. It's okay. Until the whole thing's there, Outlook's not going to ding, Gmail's not going to bing, your phone's not going to make a noise to let you know you've got an email, right? So we are flexible. That's what I would have rather said than elastic. But the throughput is stretchy. It's not that critical. Real-time audio, well, we would really like for the throughput to be in a constant range, or it's just so slow we can't get even the most compressed, intelligible packets across. Anything less than that, and you should probably just try streaming later. Or maybe you should just try downloading the podcast, because then it turns it back into an elastic thing. You can wait for it to kind of accumulate some. And it's also loss tolerant. Depends on the site. If you're running a site like YouTube, YouTube expects you to be loss tolerant. And so if you look at a video on YouTube, you may notice this if you change bandwidths a lot, but let me see if I can find one. I'm trying to find one here that's going to have some good. So I'm going to turn off the audio for a minute. Oh, I didn't do that. Like an idiot, I paused it. Start it back up again here. And okay, so I'm going to hide the announcement. So you can see what's going on here, right? You can read the StarKiss sign in the back. You can see the logos and everything, right? So we're going to change something, and then we're going to go back and do it again. Now you notice the quality had set itself automatically to 480, which isn't all that great, but I'm going to reduce it further to 144, and then we're going to go back to the beginning of this, and we're going to do it again. And can you see the logo? Can you read his name on his jersey anymore? Can you read the logo on his shirt? There's lots of stuff that says, can you see the score? So they are sending you the same size, and they're making it run at the same speed. There's the players still running, etc. But the quality, the packets have been compressed to fit in a lower bandwidth connection. So YouTube will adjust this automatically, and it did because I started off at 480, which is not the highest. I guarantee if you look at this from wherever you are, you're going to get better than 480 because I'm on a connection that's swamped with WebEx and 30,000 students, assuming you're at your apartment or something and you got faster bandwidth, which you probably do. UH has fantastic bandwidth. Compared to lots of other places. So that's an example. However, if it's Netflix, you will not tolerate it. So it's loss tolerant for real-time audio and video usually, but for a movie, it depends. You actually may not be loss tolerant at all. They may have got you hooked as a subscriber by promising you 4K. So what the heck are you showing me this old-fashioned stuff for? So TCP bundles in a variety of these things. Reliable transport, it's got that. So it will make a copy of every packet and wait until it gets a positive acknowledgement that it arrived before it throws it away. It won't do them one by one. It'll send a batch at a time to keep things going, but it won't throw anything away until it's convinced that it's arrived. Flow control is a name given to where you constantly check with the receiver to make sure he still has enough memory left to accept another batch of packets that you're about to send. If his buffer starts getting smaller, he tells you constantly, and so you will not overwhelm him. UDP couldn't care less. It'll just flood everything you give it. It'll just send it over and say, it's that guy's problem, not mine. Congestion control sounds the same, but it's different. And congestion control is meant to also pay attention to whether the packets you're sending are even arriving at the destination. And if they're arriving and there's no room, that's one problem. If they're not arriving, that's a more serious problem. That means there's congestion on the network, and you need to back off because you can quickly overwhelm the network. So TCP does not provide any timing guarantees, doesn't guarantee that you're going to get your file there in a certain total amount of time. It is connection oriented, so it does ask permission before it starts sending something. Hey, I have a user who would like to send you something. Here's his IP address. Do you have resources to allow me to connect? Yes or no. UDP couldn't care less. Well, why is there a UDP? Well, some people just need best effort. They don't care about the reliability. So an example would be asking a network time server, what time is it? If you don't get the answer back, you'll just ask again. They don't have to, nothing below has to ask if you need to get an address for a website. You can do that via UDP. If it gets lost or they don't respond, you'll just ask again. I mean, you have no choice. So, you'll just do it. So lots of things that need reliability run on TCP. Sometimes some things that need reliability will still run on UDP, even though it doesn't provide any of that, because they'd rather implement it themselves. They think they would rather implement it more efficiently in their own code than to depend on TCP's code. And that's the big decision that HTTP 2.0 made, was to step away from a lot of the stuff TCP did, because it's basically impossible to get everybody to agree to update it. They shouldn't, probably. There's web is popular, but it's not the only thing. So they just said, okay, fair enough. We will rewrite everything we need from TCP, but we'll do it exactly the way we want, but we'll make it part of our application. So we'll connect to UDP. Now, of course, the web server now at the other end, it's also going to have to reproduce what TCP would have done as the other half, right? So if you give up TCP over here, you're not going to have it on the other end either. So it was doing things for that application as well. So if you're going to get rid of TCP, you get rid of it at both ends, and you're going to have to write that. So Google was able to pull that off. They write web servers. They run web servers as well. And every browser manufacturer, of course, is going to agree to add any new protocol that Google likes into their browsers, or they're just committing browser side because it's the #1 location people go to with browsers. So security is a problem. So for security, We can use SSL. It's old-fashioned now. It's been replaced with TLS. When we get to the Wireshark labs on SSL, you'll see what I'm talking about. It's very hard to find a site because it's all been cracked at this point. All right, we have time to get into a tiny bit more, maybe a couple of slides, and it's time to kind of take a peek at HTTP and HTTP 2.0. So HTTP is something that we use to send web pages. Web pages comprise of objects. It has a base file that's in text that's written in a language called HTML, and it's sort of like taking a Word document and saving it out as a rich text format. So let's say I save this document out as RTF, and we're going to call it, let's see, where am I going to put this thing? Let's put it on the desktop, and we'll save it out here. Excuse me. I actually have another one that might have been a little easier and faster. This thing may take like an hour to write it out. It's a bad choice. Ooh, I'm having regrets. We'll come back to that in a minute. What I wanted to try to show you was what it looked like. So maybe I can pull it off. Here it is. So it's got, oh, the stupid thing actually showed it to me. It still reinterpreted it anyway, which is not at all what I wanted it to do. Yeah, I may crash and burn on this because I know it's exactly what this is going to do as well. It's going to do exactly the same thing. So if I switch this back to plain text, here we go. Yes. It stripped it all out. So what you will see in an RTF, it will say things like font size 3, font style 4, 12-point carriage return, indent left 1/2 inch. It just sort of spells it out right along with the text, and it'll put it in things like bold, and it'll type it in there. So it's human readable. That's what HTML looks like as well. So if you look at the source for a page, very often you'll be able to see that it looks like, you know, something along those lines. Okay, let me get back over to the web page. I will find one. That's it's sort of, we've gotten too smart for our own good because all these programs, they won't really show me the RTF anymore. Dang it. They've tried to reinterpret it. So objects that are on the page are referenced by that base text file. And so if your web page has a link or a picture or an applet or an audio clip, a photo, a little New York Times logo, for example, things like that, all of those are objects added to the page, and they're referenced by that base file. And the base file will say what the object is, and it will tell the user what to do with it, tell the browser what to do with it. Render this in this size of a container at this location on the page, you know, down 2 inches over 3, and it's a 640 by 480 image, and so it'll pop it in. And when you see web pages being loaded, you can see individual objects coming in. So if I go to the New York Times, which is like super busy, you can see things show up in phases. It doesn't all show up at once. So these are all things that are objects that are being pulled in from other places. If I look at the source code for this stuff, and I know there's I can never remember the keystroke, but there's one that'll view the source. You can kind of see, but there's so much Java on these things as well that it's sometimes you look at it and it's like, this doesn't look anything like what I was expecting. So the URL is basically a host name followed by a path. So that's the basics. So what HTTP's job is to try to get things back and forth. So we'll start from there next time. This is the day when we end a few minutes, 5-10 minutes early, but we're ahead of the curve, so we're doing great. Keep eyes on homeworks and things. I'm still cranking stuff out for you guys, and I hope the Saints win the Super Bowl. If you're a football fan, you'll know exactly what I mean. Have a great weekend, everybody, and I'll see you in class on Monday. Okay, go to preferences, open, click display. Yeah, there's a keystroke afterwards that was like super easy, but yeah. Tell me, hey, Henry, tell me when we're in class to come up and show me. So maybe after the 50th time being taught, I might actually remember. All right, bye, everybody. I got to run. See you later.